21st March 2023, Seattle, Washington, USA. Reading again from Nonlinear Electromechanical Effects and Applications of G. Maugin, a Frenchman who's very, very famous and will furthermore be more famous in future days about his developments in the theories of nonlinear analysis, which enable us to arrive at various solutions to what are called the theories of potential with regards to the classical theories and the linear theories. One hopes that by working through a development of a narrative, of a curriculum, of the establishment of this particular setup of electromechanical effects, that he helps explain that in the intersection of three sorts of fields, electromagnetic, kinetic, and the impulse, and their classical and potential fields, and the thermodynamic and what is ultimately a field of potential of the thermodynamic that with regards to heat and light and electricity and motion and magnetism and kinematics and kinetics or the inertia and momentum of the things that we can arrive at for Newton's laws and Maxwell's laws and Kirchhoff's and laws, for example, of Ohm and Kirchhoff, active and passive circuits, and such notions of Faraday and these other schools of men who become what are the touchstones of various theoretical developments, and that then in the lettered fields of electromagnetism and then for the mass waves and the impulse of massy bodies and classical mechanics and relativistic mechanics, and then for how heat works, and that then there's in the milieu also a usual reverberation of sound, that all these things come together where Maugin has put together at least the electromechanical, these nonlinear applications effects, in a milieu where other things are held constant, that he's able to explain then that these formulas which we're able to arrive at via the application of algebra to given particularly well-known features of these systems, that after symmetries and conservation laws and those of what we may write as continuum laws, that these theories of what are fundamentally from the theory of atomism, the atomic description or particle mechanics, the quantum mechanics, which are particle mechanics enriched as with statistical descriptions of how they behave or appear not to in the mysteries of particle physics, that we arrive in what's this linear curriculum, a development of the linear algebra and the formulas that so have finite numbers and quantities, what represents this full theory of potentials, and how it so arrives that according to basically a model of a well, in terms of when we talk about a model and a mathematical model, and then how that interprets the physical model, that we have a physical interpretation of our mathematical model, or what observable events we attach to the aspects or features of the objects of the model, that then we can arrive at a sort of fuller understanding of, for the fundamental theories, which are classical for what we can measure and observe, the observables via available physical experiments, and as to, for example, why a tabletop stands on at least three legs, or something along the lines of that Coriolis force is something we can observe via a meteorological observatory. That then as a result, so we can get into some more of what goes into and what we can take away from these models of systems that so reflect above the logical, but in the physical, how we can call that science, and also that we have not just an experimental science, but a fundamental theory of the science, and how it's so particular that the ubiquitous success of mathematics is a key touchstone of modern science, or as they say, quantum mechanics is never wrong, we're just not doing it right. That then we can arrive at something along the lines of a fundamental theory as from a monism, and that's really kind of my goal in research and study, has been almost completely in what's called mathematical foundations, of logical foundations for these technical philosophical foundations, what result physical foundations, which is altogether called foundations, and represents fundamental theory that happens to also matter-of-factly be matter-of-fact. So yeah, the other day I mentioned particle theory of electrons and Leonard Weichert and these formalizations that allow us to analyze the motion of electron, or rather the lack thereof of an electron holes in the passage and the transition of electrons as they jump back and forth as readily the missing part moves along, which represents in a mass or aggregate of these in the bulk, that it represents a current as a quantity over area. A current is as through a particular cross section of a medium. That we can talk about what a particle is in an atomism, and that then when we talk about surfaces, that those basically represent two contradictory concepts. One being the point-like, and the other being the boundary. And there's one thing to mention earlier in this speech. I had said something about Brentano, and Brentano was simply a famous logician who really brought forward the theory of boundaries when talking about set theory and partitions and this kind of thing. And with regards to topology and the notion of the point on a line and how they're contradictory, and that it was not he who was burned at the stake by the Spanish Inquisition, but 400 years earlier it was Giordano Bruno who was burned at the stake by the Roman Inquisition, who had besides that, he had written a book after the Copernican revolution where we established that it was actually the sun was the center of the solar system, and we saw science writ large leave behind or aside the notion of the immobile celestial spheres we inhabit as observers on the Earth. You abstractly are the center of the universe and the center of the world still. That after the Copernican revolution, Giordano Bruno had wrote a book that basically suggested the universe must be infinite, and that it was only later that there was books arise like, what about if there are infinite worlds, how could it not be that another one is just like this one, and this kind of thing. And then though that it said that was not heretical per se, but rather that much of his other works basically rejected the rest of what was the accepted dogma of the time, causing a very strong reaction in terms of the stories of Giordano Bruno, which you can study for yourself. And I was just reading some Descartes, René Descartes. I began to read his Discourses, and he basically outlays to describe how he thinks and to carry on about, as he calls it, just a story, in terms of otherwise that is his dogma. And if there's one thing about dogma, is that it's a constant, and over time it changes. The modern dogma of things is our scientific dogma and such. And it's a monism here, and so for me that's compatible with my monism and belief. That then René Descartes carries on in a similar way as kind of the opposite, because what he was able to do at the time when Galileo was being banned for ideas that were deemed too dangerous in a sense for their time and place, yet later on have been carried on as truth, that in the era of Galileo, or the early 1600s, that Descartes was able to wrap together these notions on the meditations and to pull together his way of thinking, and that he was able to thus curry significant publication, and over the course of time it became that Descartes is much the most famous, and partly for his concise and clear and comprehensive thinking, and that he matter-of-factly is abstractly maintaining and entertaining a conscientious dialect. That also he was political in the sense that his stratagems and tactics in the the long game and the mid game in terms of a strategy, which has an openings and a mid game and an end game, that he was able to then carry those meditations on his discourses into also then his other scientific researches, which at the time were an outlet of his creativity. Thus, he was able to combine his technical know-how and the fact that he lived a life of leisure and otherwise was largely able to study what he saw fit, of the autodidact, one who teaches oneself, the autodidact, that it became that Descartes of that period afterwards witnessed more of the Enlightenment and these sorts of things after the Renaissance then, and what became the scientific stuff after like Hooke's law, who was a neighbor of Newton and this kind of thing, that it works out then about 1650 to 1700. So that leads us forward several hundred years, and then when we start talking about this particle notion of the description of the fundamental substances of nature, on the one hand we have it down to electrons and photons and atoms, and then that being submicroscopic, that which we can see in diagram according to visual images, that in a sense, those are theoretical only. That is to say, though we're able to, in certain particular experiments, manufacture as a sort of, a magnetic pincher of an atom, or that when we are able to see blitting on the screen an output that represents, according to its energy and its discrete energy, one electron, that we get to defining why these substances and quantities in our elementary atomism is yet an approximation of the continuous theory of the continuous substrate of the background of motion, or space, in our continuous forward quantity called time, and that the relation between that and higher level concepts like the molecular chemistry, or for example that of, after the particle wave duality, particles and waves as the real thing, and then as above that, this wave and resonance theory, or what were for the early quantum dynamicists spooky action at a distance, all result as being explainable and having a common mechanism and a common determinism when our mathematical models are so equipped that they support the full range of declaration of the objects necessary to explain then these what in extremis we can only mark as a point or theorize as a certain band of fixed quantities after the ultraviolet catastrophe. That why when we talk about the Planck length and it being just twice as much smaller than an atom, than the electron is to the atomic nucleus, and that the electron in the modern apparatus is more than less the smallest particle that can be dealt with at a time, where quarks and such and even more vanishing the neutrino and what are called virtual partners of particles are even less possible to find as points, that are point theory or pointillism as a way of drawing things and a way to make a continuous tone image has that the conceit that it is for this sampling, measurement, and observer effects, why continuum mechanics is really the thing, that quantum mechanics is never wrong because it's a pointillism as we attain to a continuous tone description of an equation, a formula that arrives at reality. So that being kind of the background of a philosophy of science, and after geometry, a fundamental physics Then Maugin begins on page 43 where we left off after a description of the linear equations of wave motion through his configuration space. A nonlinear equation. The nonlinear contribution in equation 2 reads, this quantity that is a partial differential of the stress tensor Ij, that being Paoli-Kirchhoff again, super NL, taken with respect to x sub I, equals yada IJKLM, so that must reflect about the same as the Christoffel tensor of dot u k comma l u m comma n, or those two quantities as about those k, l, and m and n, their indices, basically gathering the rotation of those terms. That, comma I, plus delta I, j, k, l, m, and p, q, or around those 8 indices where we see what's called combinatorial explosion. That it's one thing when things are 1 to 1, but as soon as they're 1 to 2 other ones, then there's 6 combinations, and so on, that there's n factorial combinations of things, or the permutations. When we talk about permutations and commutations and what's called combinatorial enumeration, or reading out each possible combination, that a combinatorial explosion is what happens when we start to write these terms, as there are so many of them. That plus delta I, j, k, l, m, n, p, q, quantities u, k, comma l, u, m, comma n, u, p, comma q, comma I, that this is the nonlinear contribution, and so he might be implying that this is after and including the linear contribution. This can be represented with the help of equations 2.10 and 2.12. And so one way to think of that is that this contribution, according to these various things, is whatever's left over after the initial approximation. When we talk about an approximation, it's a function that's almost exact, but it has a little error term applied. And when we look at all kinds of methods that are kind of like, when we compute the value of the kinetic energy of a particle, like Einstein does, and you compute the infinite series, that's the Taylor expansion after Maclaurin and Taylor, who found ways to write any given formula as an infinite series of terms, where the first few terms are what are called the dominating terms and contribute most of the value that's close. And that E equals mc squared is simply the very first term of that equation. And we're familiar with that E equals mc squared is really E equals mc squared, the first sum of the Taylor expansion, the rest. And it's kind of funny because the rest of those don't have units to add up, where usually we can only add terms of like units. But those are basically those higher order contributions, or what we call here similarly an analogy like these nonlinear contributions as so. So this can be represented with the help of equations 2.10 and 2.12, which were the 3 elementary eigenmodes in the scalar displacement in terms of the curvilinear abscissa. One obtains thus that this quantity equals the sum, as from adding up the eigenmodes, alpha comma beta, of quantity yada IJKLM and ML, MN, LK alpha, LM beta, U beta, U alpha, comma I, or in that term, where this is basically the contributions each that are left off. When he puts it in a box, he's got something left over. This is what there is. Plus sigma alpha comma beta comma gamma, that must be gamma, of delta I, J, K, L, M, N, P, Q, M, L, N, N, Q, L, K, alpha, L, M, N, beta, L, P, gamma, U alpha, U beta, U gamma. So here he's describing that in the construction of these terms, he's made a sort of linear arrangement of them, that the product is evaluated, usually read left to right, but we almost always must consider that the middle terms are in the middle, and that it either is or isn't commutative or abelian, thus that we can read it the same way, right to left or left to right. that here, when it's like to so, it's accordingly that these terms represent the ordering of these evaluations from all the tape measurements, as it were, the observations, measurements, and sampling around the sides, that then we're able to add up and gain this nonlinear higher order contribution. And he mentions this as from the director cosines, what's left over and out from those, that thus we might read from Maugin that he's indicating that from reading out the director cosines of those eigenmodes and amplitudes, that it so follows that when we look to reconstruct the signal after those being put back together as by sums of elementary functions like or like sine and cosine, sums of functions that are elementary in the sense of adding up to another formula as by an infinite series or simply as by a linear system of finite terms of a series, where elementary is a reserved word for functions that distinguishes those that, according to Ruffini-Abel theorem, are able to be solved as of quintics or not. That projecting that it's so arrived at, he's basically described a way to write that everything left over is a nonlinear contribution, but it doesn't necessarily say that the way the real nonlinear contribution, which may be asymptotic or as singular, that it does or doesn't add up in terms of those, or that the terms might not be able to be replaceable or cancelable according to algebra 1 apiece, but it's according to the quantity that they come together and represent a thing. Projecting now this nonlinear contribution on either one of the eigenmodes, we obtain a propagation equation. Propagation, how things move in waves, in the following form. This rho sub r u umlaut alpha, which is the original wave motion categorized as through the region, equals gamma sub alpha u to the alpha of comma abscissa abscissa, or the drop of the line, and where it lands to. It's not a usual operation of sorts in functional theory that is otherwise not really maintaining the higher order space necessarily in a coordinate space, but here it just describes it. That's our projection space, and that's how we pull back in a sense. Again, not to conflict with existing defined terms like pull back and push forward. That's what so results that that first term plus the sigma in the eigenmodes, I imagine b comma gamma of big gamma alpha beta gamma u super beta comma abscissa u super gamma comma abscissa, that quantity comma abscissa plus the sigma beta comma gamma comma delta, which might help introduce why that the Greek letter delta is used as this index here, is according to the index notation in the Latin and the Greek. That's from the earlier section, why that is the index of notation according to its placement, where otherwise the Kronecker delta is having its own indices. So thus that whether it has indices indicates that it's not an index. That quantity times delta, or we might say del rather, or nabla sometimes, alpha beta gamma delta of u beta comma abscissa u gamma comma abscissa u delta comma abscissa comma abscissa. So that is defined as the propagation equation, and it's in terms then, if we look back, there's a curious matter that gamma was so introduced only here as for this contribution in terms, or as to why it's only is about the higher order term, or that I'm hypothesizing this in my reading of it, where we have set, and that he's defined these as the constants or the bounds, and it's only so in regions where these also hold, like y is not 0, so you can divide by y freely because y is not 0. Gamma of alpha beta gamma equals gamma big gamma ijk lmn. Then the 3 L's of super beta, gamma, alpha in K, M, and J, and the three M's in L, N, and I indices. So he's describing the gamma, which we may recall by flipping back and consulting the previous page where it was written. The gamma, after the Piola-Kirchhoff tensor, where the original big gamma was written and the original little delta was written there in those terms, and that the acoustic Christoffel tensor is this gamma. Is this other constraint that's defined in terms of the Christoffel signature, CINKL, CIJNL, and CIJKMLN. Or rather, that's that big C. That it's defined in terms of what holds in terms of the original assumptions he made about what holds in the description of the linear wave equation and its propagation. That the second condition he's written is delta alpha beta gamma delta equals delta, little delta, I guess you might write, IJKLM and PQ, again those 8 indices of the 4 L's in beta gamma delta alpha rolling around, being modular in a cycle in a sense, in terms of that things are in a linear order in their evaluation as according to taking the cross or maintaining a consistent way of the right-hand rule to read the next index of rotation in this orthonormal vector bases that are ordered, that they come around again, and being thus modular in a sense, enclosed or circular or cyclical. Those in the indices K and PJ, and the 4 M's in LNQA. Again, having figured out that these are the terms that were left over, those basically that come around. Therefore, the nonlinearities cause a mutual coupling between eigenmodes, case where beta and or gamma are different from alpha and beta comma gamma and or delta are different from alpha, as also self-coupling of each mode for beta and or gamma equals alpha and beta comma gamma and or delta equals alpha. So he's described that there are at least 2 cases, kind of like the case where something might be an asymptote or it might be a circle, or that there are 2 general modes expressing why something's not globally so, that there are local minimums about either one of these 2 conditions. Or here that the mutual coupling is between the eigenmodes, and we might call that part of harmonics, where harmonics are what all adds up from these things. And that self-coupling is in terms of the separable and composable with respect to that there can be kind of an external coupling to outside forces and an internal binding of inside forces. Reading back into that we can talk about that in terms of kind of an abstract inner and outer product, these 2 couplings that describe what he calls collectively the nonlinearities. Everything else being so defined as containing the approximation or the method or the arrival at that linear equation. At this point, the following remark is of importance since it will greatly simplify further considerations. The 3 eigenmodes are orthogonal and propagate with different velocities. Therefore, when one vibration mode is piezoelectrically excited and the other modes correspond to eigenfrequencies, which are sufficiently remote from the excited mode, the latter is preponderant, and couplings with the other modes correspond to corrective terms, which may be neglected. So here he's basically saying that these are my nonlinear functions, and there's a nonlinear part to it. So this is only not the nonlinear contribution that has been able to be contained and encapsulated in terms of some of these settings, and what Maugin here is carefully describing is that outside what we have built, there is a wider world of these things, and that in these higher order harmonics, that is so defined that he's providing us the justification for him to have made room for the alternatives in the case that otherwise one would wonder why he had left out such a thing. And here he's just describing it in terms of these wider systems of all the different kind of fields, this development so far in the combinatorial explosion of all its terms has only arrived at, and it's a great thing, all the linear contribution of these terms and then all the nonlinear contributions of some of these other terms. The mutual couplings and the self-couplings of the eigenmodes as about the harmonics and the internal frequency packet. Therefore, on one vibration mode is ... this corresponds to the working hypothesis of a monomode process. So here the monomode process then is a particularly built-up thing that he's able to say that it's just kind of like a higher order construct of a linear notion. It's at least one build-out setup of nonlinear contributions. This corresponds to the working hypothesis of a monomode process. As well, it might be reflected that when we talk about the mode of things and the modality, that the mode represents usually in a given system, a given dynamical system. And with regards to, as we were talking about a little bit before, about the astable and equilibria and local and global minimums or maximums, basically global minimums of potential that are stable and equilibria, that the monomode process represents something that in terms of however else it might be so dynamic, and that in terms outside these terms or outside the box, there would be other ones. I think that what this word represents when we say a monomode process is that a process is over time, everything's universally parameterized by time, and that the modes of a process are how something is behaving or in what regions we may expect to find something in a given amount of time, like according to the dynamical models of epidemiology or the dynamical models of weather or the dynamical models of pretty much about anything, network analysis, traffic analysis, the dynamical models, and then we talk about the ergodic and what that does over time, and random motion, Brownian motion, Gaussian motion, and these hypothesis of small perturbations, and all these sorts of Monte Carlo techniques, and Markov chains, and that these days a lot of it is written in the Markov models. Here he's established that basically this is so far what peak we've reached, and that this is how he's then so described that so parameterized by time, these dynamical systems, this wave propagation is a process defined in terms of time, given parameters, having values at any given time according to parameters. In this condition, only the terms corresponding to alpha equals beta equals gamma equals delta in equation 2.18 are kept, and the latter equation takes on the simple form, no summation over alpha. Here he's basically reduced the same, now we've made things spherical, or it's in the box. And because the fine transforms and the transforms that presume and preserve all the topological character are held together, that applies for other shapes, but it's really now, again, that he's kind of, again, just noting that it's necessary to consider that all this wonderful predictive ability and the formula is formally only good in the box, that the rho sub r u umlaut alpha minus gamma sub alpha u sub alpha comma abscissa, or establishing the continuity condition, or where that's zero, equals gamma alpha u alpha comma abscissa squared, so gamma alpha of the u quantity squared comma abscissa plus del or delta or nabla comma alpha u alpha comma abscissa cubed comma abscissa. So in this sense, he's written out that the error terminus sense, or after the approximation, or what's left over after the contributions, is in this third order, which is basically after what is the sufficiency of the three eigenmodes of the function of the fact that our system has three dimensions, that according to the eigenmode problem, that is the characteristic of the order of the rank of the term that so reflects this difference between these quantities when the particular terms mentioned equal above are kept. So there's another page or so. So that's about up to formula equation 2.20. And I'll set that down for a moment. Let's see. And then what then in looking back, then that talks about a couple different things with regards to the discussion began with just kind of overall discussion of continuum mechanics and the fundamentals, and then that we got into particular Maugin talking about the nonlinear contribution and how we have this linear methods and numerical methods and methods that arrive at there's sometimes perfect methods and there's sometimes approximations, and approximation is to the proximate, to the close, to the near. And for example, in mathematics, the limit is the sum of sorts of all the partial contributions that add up to the term that has a value of the limit. Like the inverse powers of 2 adds up to 1. Or the otherwise that their infinite series is well so defined, so it's possible to arrive at something like this infinite series if you keep all its terms in order in the telescoping, maintaining their index, that the infinite is the otherwise unbounded, and as soon as you introduce anything else out as to a meter of it, that it's so bounded by the units of this infinite increment of sorts. Being careful that infinite increment is a non-standard usage of a term. That in the numerical methods and the linear, then as we begin to describe these nonlinear contributions, that these are essentially the significant parts that may have a non-zero contribution that are left over from the linear, that in a linear we usually may neglect because, well, we'll just build it twice as strong and figure it'll never, flow over twice as high. Then when we think about something like the rogue wave, which is on the surface of the ocean, every now and then, a given chance and circumstance, there'll just be a giant wave out of nowhere. Or anything to do with what would be something outside of the mode of the process, without otherwise affected. Those are contributions either externally or as internal energy and internal frequency, or as of external energy and harmonics in their construction. So we got into that a bit, and it's quite ongoing. And then, this is another book. And this is a book, then when we talk about electronics and electromagnetism, this book is called A Reference Manual for Telecommunications Engineering. It's got, it's from Wiley Inner Science. It's got about 1,500 pages, and the index begins on page 1471 and ends on page 1504. So there's about 31 pages of index, and there's about 100 terms, so there's about 3,000 terms in the index of this book. And he talks about, a root mean square. Root mean square is a way when we're computing this phase and these things in electromechanics that we have arithmetic means, geometric means, and harmonic means. Most people are familiar with the arithmetic mean. That's called the average. That the root mean square is then when we talk about these halving and doubling spaces, that it's root mean square. And then he talks about peaks and density. This is under the section 26-7, conversion of power density to electric field strength. And here he gives the units. And this is a pretty fantastic book, and it's basically all of science and engineering that could fit in a book. That in the middle it's got, Intelsat 4A and 5 transmission parameters. It's funny that most satellites in the sky, you can point a dish at them and download their link if they're just communication satellites. They're just sitting there open. In the old days, they say, for dish, you got to get a converter and encryptor card, but that's kind of after the fact, really. I mean, there's all kinds of just standardly compressed and encoded data right off the air. And otherwise, this book, and it says by Roger L. Freeman, describing all these things that come from the International Telecommunications Union, ITU. There's ISO as International Standards Organization, then ITU is the International Telecommunications Union. And so ITUT is the section in ITU for telephony. And there's other ones like ITUX and for various things of the International Telecommunications Union. And this was almost originally after what was called the Consultative Committee of Telegraph Technology or something, the CCITT, the Committee Consultative de International Telegraph. And that's where we got facsimile and all these standards of the, from before that was dual tone multi-frequency, which is these harmonics in tones that are regularly assembled from very simple crossings of wires given resistors of various weights that results that with 3 wires and 3 resistors you can construct a touch tone phone. And that these kinds of things work up then in terms of like, oh, the ringing amperage of a phone line is it was pretty high. I mean, if you happen to be holding the phone line and when it rang, it could shock you pretty good. But that the low level operation after the ringing voltage is much less in terms of reaching the signal and point of presence and telephony as it's implemented in the what's called plain old telephony system, according to what's today called the fiber backbone. That all the phones and all the things work according to how all these different systems of fiber optics and copper and microwaves and transmission media, and here we've just been talking about the transmission media and propagation of waves in the radio frequencies and in the signals, that all this results then basically an outlay of engineering of signal analysis, which is then a field of mathematics called signal analysis. And that signals engineering then is what arrives at that the feed and the cats and this sort of thing. So anyways, that's a pretty great book. I acquired it some time ago, and every now and then I look through it, and it reminds me also of this fellow's there's a modern book called Digital Telephony. And digital telephony explains stuff like signaling system 7 and what is the backbone of modern telecommunications engineering as according to standards, vis-a-vis that anybody can build a crystal radio set, and then there's what gets into standards and regulation in terms of that bandwidth is a limited resource, and then that we might later get into why there's just as good an idea to have a Clean Air Act like cap the coal smokestacks and a Quiet Air Act as in 5G is not good for everybody. But anyways, that's what there is for today, and I hope you have a great day and good luck.